You see, there is something called locality of reference. Okay, locality of reference means that it is an observed fact that over a short period of time, the addresses that are generated by a computer program, okay, those tend to be localized. That means what is meant by localized? Localized means they are nearer to each other. Okay. For example, if you want to have, say, this is a memory space. Okay. These are all memory lines. If one piece of data is, say, here, another piece of data is, say, here, another piece of data is, say, here. Okay. And against that, if some other piece of data are arranged in such a way that one piece is here, one piece is here, one piece is here, one like that, these are more localized, okay, than these. So locality of reference actually refers to the fact that when we are locating some, reference means referencing the data. Reference here refers to referencing the data in memory. Now, when we are referencing some data in memory, okay, then how locally are these associated? That is locality of reference. It's as simple as that. Now, when we say that computer programs tend to generate localized data, that means that over the time, over a short period of time at least, the data that is the data addresses generated by a computer program for storage, etc., tend to be like this, bunched up locally, almost locally. Okay, and it is true that over time, this localization or this locality of reference is going to be slightly disturbed. The reason for that is that when you are allocating memory, say for example, you are allocating memory spaces, your program is allocating memory spaces, it goes 1, 2, 3, 4, but immediately afterwards it finds some other data. Okay, so what will it do? Will it actually overwrite the data? Of course not. This is required by some other program. Of course not. So it will allocate it here, and here the locality is compromised. I won't say it is lost, I'll say it is compromised. What is the difference between compromise and lost? Well, this is not exactly local, is it? It is not around each other, but this is as much around each other as possible. So I will say locality is compromised here. Now, why these kind of things? Well, why this locality of reference, why this actually happens? There are two main reasons for that. One is spatial and one is temporal locality. So imagine, uh, especially those of you who have already done um, assembly language programming, you will be able to understand this better. That uh, just one sec. That let us say there is you've got a pair I1, or rather say I and DI. Let these be the instruction and data pair. Instruction and data pair. Now you see instruction and data pair, and let these together be 4 bytes. So instruction and data together making 4 bytes. We may call this a 4-byte instruction sequence. We have only done up to 3 bytes, but let's say we've got a 4-byte instruction sequence. Now, in that case, if II and DI are located in, say, memory address 0xFF00, and we have byte addressable memory, that means each byte can be addressed, or they have addresses and each byte can be addressed. So, if II and DI, if they reside in 0xFF00, then the next I2 and D2 in that same sequence, in the same series of instructions. What I mean by that is it can be the same function, same loop, the same block, whatever. So this I1 and D1 located at this, and I2 and D2 is most likely to be located in OXFF04 because the difference of these is 4 bytes. So the first instruction and data, followed by the next instruction and data, followed by the next instruction data. Next one will be at OXFF08. Next one will be at OFXFX. So that will be OX. So can you tell me that? Okay, see, can you all tell me that this I3 and D3, they will probably be located in OXFF08 because that is obviously a 4 byte instruction. Can you tell me what will be the location of that? Location always means the starting point. I4 and D4. Who can tell me? Okay. So I1 and D1 is OXFF00. I2 and D2 is OXFF04. Okay. OXFF. You're saying 0C. So 8, 9, A, B. Very good. Good. Well done. Is that true, Amrita? Yes, of course you are. So, okay. So this is what it is. Now you see, this means that I'm at towards program. Say if this is the first instruction and data pair, this will be and let's say this is 4 bytes. Then this is going to be the second one, the third one, etc. This is going to be the fourth one, and then it has got some more data, so it will jump to say here. And if this, let's say, this is 100 bytes or whatever, so this is going to be OXFF0C plus 100, whatever that makes. This will be in hexadecimal. So like that. But these are all located nearby each other. This is called your spatial um, locality. A spatial locality, simple spatial locality, locality of space. Because of the arrangement of instructions and array. See, if you're not arranging it like this, it will be very hard for the control system to for the control unit to work. So what does it do? If you remember this, is that got a program counter. Okay, so the program counter always contains. So if the program counter at first contains, say, OXFF00 and it is fetched, and as soon as it goes out, the program counter is incremented by 04 to make OXFF04. This is the next. When it is gone, again this is incremented by 4 to make OXFF08. That's why it's called a program counter. It holds the address of the next data. Now this has to be properly automated, and the only simple way of automating it is if you are maintaining an incremental relationship, a simple incremental relationship with the previous address. For example, if the PC looked like this, first it had OXFF00, then it had OXEEC1, then it had OX0018. All of these Can you find any relation between these three? The answer is no. There is no pattern. Here there is a pattern. This is plus 4, this is plus 4, this is plus 4, so on. Here there is no pattern. And so, because here there is no pattern, and then obviously you cannot automate this process. Each time you have to provide what is called a jump instruction to this. Again, a jump instruction to this. So a program will be a series of jump instructions. And there also heavy amount of sort of administrative work regarding the memory addresses has to be done. For example, here, so from here it jumps to this one, but to the programmer, this is nothing but I5, this is I6, this is I5, this is I6, I5 D5, I6 D6. But there is a gap of so much in between. So we divide the address space between logical addresses and physical addresses. And there is obviously is a mapping, which is a function. No matter how simple it is, it's a function that maps the logical address to the physical address. I'll call it FLP. So this FLP, it maps logical addresses to the physical addresses. Okay. And this is necessary because you see logically this address is coming after this. Physically there is a difference because there is some data in between. Obviously, if the operating system thinks it is okay, then it will move this data somewhere so that this can be continuously allocated, but it is not always the case. It cannot always be done. Sometimes moving this data would create more problems than it would be useful because it is obviously being used by some program. So um, uh, it will be more problematic than useful. Hence, it follows that this logical address, that is, this is say x and this is say x plus 1, has to be properly matched to the physical address, that this is OXFF0C and this is OXFF0C plus 100. This is the physical difference, so it has to be mapped onto that. So memory designers must take this into consideration. Nonetheless, so this is special locality. Now, so that is why it makes sense to transfer a block, not just a line. So that means that when you are transferring, see why we are transferring, because say there are levels m to n of memory. Well, let me show you the Hayes book once again so that you have a diagram there that you can notice. Look at this. This is the processor. Now, in these various levels of memory, it cannot, sorry, this is getting out of focus. This is getting out of focus. Sorry, just one second. Yeah, that's better now, I think. So here, okay, this main memory bit and this cache. Level 1 is always on board. This level 1 cache, there is a difference in this logical diagram. Level 1 cache is always on board the CPU. Level 2 cache is there, which is a go-between in the main memory and that. And the main memory can be of several different. And then the secondary memory. And main memory can be of several different layers. Looks basically like this, that you have a, say, okay, let's say this is a CPU. Oh God, yeah. So that's better. Let's say that this is the CPU. So control units. Just one sec. Just bear with me one sec, please. Yeah. Okay. So let's say that this is a C, um, ALU. The registers. Now here there is something called a cache. This is level one. This basically is on board. And level two is there, which is outside it. Then there is main memory levels, M1, M2, etc. Shushma, you want to say something? Yes. পেজ নম্বর কিসের পেজ নম্বর? বুকের পেজ নম্বর এখন দেখতে পাচ্ছি না, ওটা মেমোরি অর্গানাইজেশনে আছে, দেখো হয়ে যাবে। এখন বুক না দেখে এদিকে দেখো। হুম, so there is M1 and then up to M2, then up to Mn, then it is there, and then there is, so, two-way relationship, and then there is secondary memory. Now, as we discussed earlier, I'm just discussing it for the benefit of the new people, that CPU cannot access any of these memories directly. It can go and access M1 only, and it can directly access cache in particular, you know, implementations. It can be both. It can be that it has to go through the cache, or it can be that it can directly access both the cache and bypass it also sometimes for the main memory. But if it goes into the main memory, it will always be in level 1. Level 2, level 3, etc., up to level n are totally outside. What happens here? Because this way cost is increasing, so is speed. This way cost is decreasing, so is speed. This way size is decreasing, this way cost is, this way size is improving or increasing, right? So what happens is, whenever you want something and it is not in cache, it is fetched from M1 or M2 or M3, or if it is directly accessing M1 and it is not there, it is fetching from M2, or then, or if not, then it's fetching from M3, like that. So basically, a data which is residing in secondary memory is transferred to MN, and MN has all the data which is necessary. If it doesn't have the data, then it has to page. It has to page out. Pages are basically blocks of memory that are transferred. That has to be going into secondary memory, and that is brought into MN. So a new one is brought into MN, and then this one is propagated through this. When it comes to M1, then level 2, then it goes into CPU. Okay, so this is what happens. Hmm. The cache is, what do you mean? What do you mean by that? Sorry, come again. Level 1 is on board with the computer, okay, which is with the CPU. And level 2, main memory, level 2 is just outside it. Level 2 is just outside it. It is obviously on the motherboard, but it is just outside it. Okay. No, no. Level 1 is obviously, definitely, the registers and the level 1 are together, right? Basically, the logically we can say always together. Physically, if this is the CPU chip, then this will be this can be level 1 can be the registers. It can be just a small associated chip with it. It still be one chip basically in one integrated circuit. And this is for the internal use of the CPU's core, and we cannot access it. Then there is level 2 cache, which is larger than level 1. Okay, but it is cheaper and slower, and that is kept outside of the CPU. But that CPU, now where this is fitted, that is totally dependent upon the system engineers, which we don't know. It may be on the motherboard, it may be somewhere else, but it's generally on the motherboard, obviously. Generally, everything that is together, this, for example, the RAM slots and everything, that is all in the motherboard, isn't it? So it's all in there. But it is outside the CPU. So the CPU accesses that for data, and if it is not in there, it's called a miss. If it is missed, then it goes and looks into the main memory. So from the main memory, level 1, it can be like this in architectures. Some architectures, if it is not in level 2, it goes and seeks it out in main memory 1 and gets it from there if it is there. Otherwise, it is moved from there to here, then it gets it and makes it available in cache also, so that next time it doesn't have to access M1, it can get it from cache. The reason it doesn't want to access M1 is because it is slow. M1 is slow. M1 is faster than M2, which is faster than M3, etc., etc. But M1 is also smaller than M2 and more costly. M2 is smaller and more costly than M3, like that. So the reason it doesn't want to access any of the M levels is because it is, if it directly accesses main memory, it takes a lot of time. It has some idling issues, CPU idling issues. So it wants to go through the cache. Now, if it is not found in cache, then it goes and seeks it out in M1. Now, in most cases, this M2 to M1, MN, it is basically, it may not even be there. Well, I mean, for our purposes, when we are looking at things, to keep it simple, we'll only be dealing with level 2, M1, and then secondary memory. Okay, but that is, uh, in real life, there will be several levels of these memories which the computer has to seek out the data from. And the data is percolated downwards or upwards, however you see it. If you look at this as upward percolation, then upwards from Mn to M1, and then the CPU gets it. So the idea why we are dealing with this is, the idea is to keep as much of the data next to be used in cache as possible. If it is not available, at least it should be in M1. Then if it is not in M1, at least it should be in M2, like that, like that, like that. Now, if the data is not in L2, we call it a cache miss. And it's an expensive issue. Then you have to go and access the M1. And so the data is not in M1, and again, that's another issue. Then you have to percolate it forward. But once the data is there, it is then transferred to L2 also. But transfer, obviously, you mean copying. What do I mean by transfer? See, this is a pen. I'm transferring it from here to here. The pen is not here anymore. Okay, the pen is coming down here. That means, or let's say the pen is here. It is being transferred to this place. That means the pen is not here anymore. It is here now. Okay, but that is not what happens with data. Data is copied. You cannot obviously transport data. You cannot do that. You have to copy. Electronic copying of zeros and ones. Level Mn to level n minus 1, then level m minus 2, like that, to level m2, then to m1, like that. So that same data is then copied into level 2, because next when the CPU, level 2 means level 2 cache, mind you. So when M1 doesn't have the data, or let's say if M1 has the data, if it doesn't have the data, it gets it from here. If it doesn't have the data, when finally it does have the data, CPU gets the data, and it is also taken into level 2. It may be that it is allowed only through the L2. So in that case, it will first be gone into first it will go into L2, and then the CPU will get it from the L2. If it is allowed to bypass, then it will get it directly from M1 without much or without further ado. But that part is going to come into L2. Understand, Amrita? See, logically speaking, it is not, but physically it might be. It depends upon the implementation of the computer. Obviously, it does. No, logically it is always the same. Now, what the electronics engineers do, it is not our concern at all because that is a different issue altogether. Okay. Logically speaking, there is level one cache, there is level two cache, then is onboard CPU registers. But a level one is always onboard with the CPU anyway. Now they might actually be the main registers, they actually might not be. But for us, when we are looking at it through the computer architecture point of view, from the programming point of view, etc., from the point of view of a computer scientist implementing a program to use or whatever, okay, then level one is level one cache on board with the computer, and level two is outside it. And by the way, level one and level two are more or less both, uh, level two especially, uh, they are both transparent to the programmer. You can access what? You can access main memory, but you cannot access the level 2 cache directly. Now, so because of this transferring issue, if you've understood this, it makes sense not to transfer just one instruction, but a block that contains the particular instruction. It looks like this basically. So you have this is the instruction IB1. Now it is generally so that we divide the memory transferring units. There are several of these, and we call it a block or a page. Now, let us say that this is the page in MI. As you can see, MI is larger than MI minus 1, which is larger than MI minus 2, and ultimately there is M1, etc. Now, let us say that this is the instruction I were looking for, and it is within this page. There are several other pages here. It is within this page, it is there. So when we are having a miss that we don't want, we don't have it, and it is in MI, and the same data is in MI, but it is not in M1. So instead of transferring just I, we transfer the block. We transfer the block from MI. It's very hard to keep it in focus. So MI to M minus 1, MI minus 1 is copied, and M minus 1 is copied like this, it is taken to M1. But there is also something else that you must remember, that almost always, which we don't want, if there are so many levels, there can be one level or n levels, we don't want these to be unoccupied. It's a waste of space. So some space is obviously left alone, because when the program is running dynamically, we may need some memory spaces. Definitely we may need, but otherwise we don't want any unused memory space. I'm not saying free memory space, I'm saying unused memory space. Even free memory space, let me make the distinction. Free memory space is something that can be used. Unused memory space is something that cannot be used. For example, if you have already done BCA or BSc Computer Science, you might know that there is something called memory holes. Have you heard of this term? Let me write it somewhere else. Have you ever heard of this term memory holes? Obviously, that doesn't mean you take a drill machine and hold the memory. No, you don't do that. Make holes in the memory. You don't do that. What are memory holes? Can anyone tell me? These are closely associated with terms like dangling pointers and others. Have you heard of these things? Very important programming concepts. Have you heard? Okay. Let us just say memory is there. Now some data is being used. Let me use a different colored pen for this. So some data is being used. Say by program 1, some data is being used by program 2, then maybe some more data is being used by other programs, like we have a different kind of a data by say program 3, so another kind of a data by program 4, and all of this is the main memory, obviously. Well, whatever memory it is, it may be main memory, it's memory. I'm not, without going into details of what kind of memory it is, it can be any kind of memory. Now let us say that, so this belongs to the same kind of programs, program 1 and program 2. Then let's say these are text data. This is a graphical data used by say program 3. Then this is, let's say this is database data used by a program say 4. Now let us say that program 3 exists. There is something called garbage collection, where the garbage collector, will term this as GC, will free this memory space. What does that mean? What does that actually mean? That means it actually trashes this part of memory. Doesn't mean it actually busts it out or anything like that. You cannot wipe out memory just like you wipe out a blackboard. No, but this is made available. Basically, this means it is made available. Let me be very specific. If it is made available, what happens? Memory is there. So this is program 1 data. These are all active now. And this is, say, program 4 data. And here, another program, maybe a different kind of a program altogether, or the same kind of a program as before, whatever it is, say P5 comes in. So P1 is there, still executing. P2 is there. And then there is obviously P4. But in between, P5 can come in. Why? Because the garbage collector had freed this space. There are certain reasons why the garbage collector will work. It has to be told that the data has been freed. How does it tell the data has been freed? It tries to see if this data can be reached by anything or not. If the data that was used by process 3 or program 3, whatever you call it, actually a program in execution is a process, so let's say it's process 3. When this data becomes unreachable, that is nothing in any of the instructions here available with P1 or P2 or P4, nothing is accessing this part. Garbage collector knows that okay, this part is unreachable from any of the programs. It is not, there is no attempt to reach it. And it can be temporarily done as well. Temporarily means time based. That means if for a certain number of cycles a particular data has not been accessed, then that can also be removed and put into the free list. An example of that, an example of that, just a minute. Just a minute. When I'll let you speak. I'll let you ask me questions. All right. Now, what an example of this is, for example, web pages or web forms. It's temporal in nature. Sometimes it will not. I mean, after a bit of time, it will just expire because those are not needed anymore. Forms, they partake of security reasons. For security reasons, they partake of things like admitting, say your details and stuff. So just entering your details or admitting them into some place. So basically, they always have to be super cautious. So after a certain number of times, it'll stop. Now you see, let us say let us say that the garbage collector doesn't get any chance of knowing that this is freed. P4 is gone. P3 is gone. But the garbage collector doesn't have any chance of knowing that P3 is gone. It is waiting and waiting and waiting and waiting and waiting. Okay, nothing happens. An example of this is what we call, it can be several things. An example of this is what is called dangling pointers. Let me show you what they are. It especially happens with C programmers when they forget a pointer. So let us say that this is memory. All these different types of data are there. Now, if there is a pointer inside any of the, say there is P3, or not any of them, let's say P3. Now, there is a certain pointer somewhere. It can belong to either P3, or it can also be, say, a pointer in another program, which is sometimes even more the case. Let's say P4. Now there is a pointer in P4 which is pointing towards the data in P3. It can also happen that there is a pointer in P3 which is pointing towards data in its own scope. Now, for example, a file. Let's say this is a file pointer and this is a file that you've loaded here, and both P4 and P3 are pointing towards it. Okay. This is scenario 1. Scenario 2 is there is a just simple P3 is there, a pointer there. So this is scenario 2. This is scenario 1. Okay. So P3 is there and there is a pointer that is pointing towards something. There's maybe several pointers are there. There's one pointer is there. When P3 is gone, P4 is still pointing towards it. No issues. Now let's say that P4 is also gone. Fine. So there is nothing pointing towards it. But let us say that this pointer that was there has not, when P3 is gone, but this pointer belonged to P3, but it is still referencing to this part. It has remained somehow, it has not been freed. If it is not freed, then the garbage collector cannot work because it sees that this part is still being accessed. So it looks like this. So because this pointer is not freed after P3 stops, it looks like this. We have P1 data, P2 data, and in red I will write P3 data. P3 data not freed because of okay, pointer not freed. Okay, and then obviously as usual there is p4 data as well. In this case, well, no one knows. So when finally p5 comes, so p5 is allocated this space and so on and so forth. But this part cannot be accessed. It is not useful. No one is accessing it. It cannot be freed also. So all in all, if you imagine that you can put a cup on a hard surface. So you're putting one cup there, 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 and there. What about this one? It's like a hole. See, we have a flat surface, and this is a hole. You can put a cup here, a cup here, a cup here, a cup here, but not a cup here. Why not? Because there is a hole there. Similarly, this is like a hole. This is where data which has not been freed properly has not been garbage collected. And so this is not available to any of the programs. The reason being simple that the system does not recognize it as a freed memory space. So why should it ever overwrite the memory space of another program? This becomes a memory hole. You see, over time, several of these holes will appear in memory. As you keep on running your programs, okay, pointers will come up that will not be freed, and those will create these kind of situations where data will not be freed because some pointer is pointing towards it. But that part of memory is no longer active. It's not no longer needed. So that is why it is very useful to take care. For example, when you're doing your C programming, when you're using specifically when using files, it is always advisable, not just advisable, all the programs will contain the freeing of a file pointer, isn't it? Have you seen this in C programs? Yes or no? So that is why it is used, so that memory holes are not created, the pointers are freed. So similarly, you have pointers which are there but they point towards nothing. Those are called dangling pointers. So there's a pointer here which pointed to an object. The object is destroyed. Okay, the object is destroyed. Then the pointer is not freed. What happens? It points towards nothing. This situation is called dangling pointers. Other issues include, there are several issues that can create memory loss. Other issues include, for example, let us say that this one here became corrupt. Somehow the data here became corrupt. So the data was copied here somewhere. Now P3 being gone, that data was effectively freed. That part of memory was effectively freed, but this one was not. It could be an issue with the system. And then this remains as something where you cannot allocate anything and you cannot even use it because nothing is using it. Okay. So now these here, coming back to our memory allocation. Okay. So these transferring of this transferring of data, it is done by not by say one instruction at a time. It doesn't make any sense. It's done in blocks. So the and why is it done in blocks? Because of the presence of spatial locality of reference. You understand it now? Because it is most likely that if I is in this block, the next instruction, say I next, say this is I1, the next instruction in the sequence is I2, then I3 and I4. It is most likely that because of spatial locality of reference, the other instructions that are needed immediately after I are going to be around in this vicinity. So if I can transfer this into the cache, okay, M1 if there is no cache or if M1 is a cache, whatever, if we can transfer it into M1 and or the cache, say, let me just draw this one here, say cache 2, and this is instruction containing I. Sorry, there you are, I. Okay, so either it'll go from M1 to cache level 2 and then into CPU, or directly from M1 into CPU, but then again it will be written into cache 2, because next time when I1 is done and I2 is needed, the CPU can go directly into cache and get I2 from there, I3 from cache, I3, etc., unless and until there is a time when again there is a miss and again some more data will have to be brought in. Okay, so this is called spatial locality of reference. It is very useful in the design of or the schemes for transferring data into cache so that it is got more readily by the CPU. And there is obviously something called temporal locality. An example of temporal locality is very good example of that is loops. What is temporal locality? Time related locality. Temporal means time. Time related locality. Okay. So what is it? Basically, it means that look at so what does it actually mean? It means that, for example, loops. Now, inside the loops, see, let us say in a one particular loop, the data looking like this. So, all the data that are needed by the loops are in blue. So, this, 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 but they're all needed in the same loop. I'll draw this as follows. Let's say there is a for loop. which uses this, and this. So it requires, and then ultimately it goes out. Now, all this data, this is this. So there is no special, so there is lack of spatial locality, because what is spatial locality? Located in and around each other geographically. That is spatial locality. Space wise. This is not spatial locality. However, it is used within the same loop. So this one is used just before this one, is used just before this one is used just before this one. There is temporal, that is time based, time wise locality is there. So time wise locality is there. Okay. So there is these two types, spatial locality and temporal locality. Good example of temporal locality is for loop. Now it is desirable to keep the entire set of data and instructions of a for loop inside M1. Now this M1 is it can mean two things. Either it is the level of memory just accessible by the CPU but not the cache, or it can also mean the cache memory in some logical uh, treatises. But in any case, although spatially these data are different, it should be contained exactly here in M1. That is the fastest accessible memory to the CPU. Otherwise, it won't really work that well at all, because inside a loop you're going to have to go around looking for those ones that are possible. So basically, it is desirable to store entire loop in M1 if possible. Okay. Now, generally speaking, then we talk about something called a currently working set. Oh, you got what have you got now? You got a class now, na? So sorry. Oh, you got a class now, guys, right?